reminders about the symmetric groups and cycle types of permutations and things like that. But we can put that aside for a little while now. So the bits from lecture 1 that I want to remind you about are really the second part, where I introduced a whole bunch of combinatorial objects. And I'm going to remind you about what those were briefly. So I'll sort of list on this slide the combinatorial object and maybe a reminder about notation, and then an example of each thing. So this should quickly remind you of the various definitions that we saw this morning. So starting then with a partition, lambda of n. So as in this morning's lecture, n will be a natural number throughout. And we defined what it meant for lambda to be a partition of n. And we used this symbol to denote is a partition of. So here's an example. So here n is 9 and 5, 3, 1 is an example of a partition of 9. So a partition is a collection of natural numbers. Each of them will be less than or equal to n. Their sum will be n, and we write them in this weakly decreasing order. So that was one thing we saw. And then we saw Young diagrams of a given shape. So the shape would be one of these partitions, lambda, and a Young diagram was just a diagram of the sort that's now displayed on the slide there for this example. So for the partition 5, 3, 1, we draw a picture like this with 5 boxes on the first line and then 3 boxes on the second line and 1 box on the third line. Okay, and then we saw the idea of a Young tableau of shape lambda. So what that was, well, firstly, a diagram of shape lambda as above, and then an assignment of the numbers 1 up to n, 1 each to each of the boxes in the diagram. So this is an example in continuing the example that I've been working with on the right-hand side on this slide so far. So here our n is 9. We take each of the numbers 1, 2, 3 up to 9, and we assign 1 each to each of the 9 boxes in the diagram. So that's what a Young tableau is. And it's not a very interesting problem, as we noted this morning, to count those, because it's pretty clear that we have n factorial of those, 1 for each permutation of the numbers 1 up to n. So finally, and more interestingly, we have the notion of a standard Young tableau. So that was, well, firstly a Young tableau as above, but then with some conditions, and the conditions are simple. It's that the numbers along each row from left to right should be increasing, and the numbers down each column from top to bottom should be increasing. So the example that I gave before here, when I just introduced a Young tableau, that was not an example of a standard one, because we don't see, for example, on the first row, the numbers are not increasing across the first row. And on the other hand, obviously, on the bottom line of this slide, I've chosen one that is standard. So if you look at the numbers going from left to right across each of the 3 rows, well, there's only a condition on the first 2 rows here, but those are increasing. And again, if you look at the numbers as you go down each of the, well, there's 3 columns where there's a condition here, and we see increasing numbers down each of the columns. So that would be an example of a standard Young tableau. So that's a recap of the combinatorial definitions from the first lecture and that we're going to be interested in. And perhaps, sorry, just before I go on, let me remind you that I introduced notation. I haven't put it on the slide here, but we were interested in the number of these things. So the standard Young tableau of shape lambda. And I introduced notation f lambda for that thing, for the number of standard Young tableau of shape lambda. So maybe I'll just say a little bit about what's coming in this lecture and where we're going with this whole story. So as I mentioned this morning, there are 2 formulas that I want to talk about for for that thing I just said, for the number of standard Young tableaux of a given shape. One of them is the hook formula, and the other is a determinant formula. And I'll introduce both of those things in this lecture with some ingredients. There'll be some definitions to understand the hook formula, for example. And then the other thing that I want to do in this lecture is prove to you the equivalence of those two formulas. And then what's coming in lecture 3 is at least a sketch proof, a bijective proof of the hook formula. And so for the remainder of this lecture and for lecture 3, everything's going to be quite combinatorial. You don't need to worry about any group theory. We'll come back in the final lecture, lecture 4, I'll come back to thinking about the symmetric group and explaining why we care about this number of standard Young tableaux of shape lambda, and the role it plays, a little bit about the role it plays in thinking about representations of the symmetric group, or in other words, objects on which the symmetric group acts. But for the rest of this lecture and the next one, we're going to sort of stay in the world of combinatorial things about these Young tableaux. Okay, so that's by way of reminders and preamble and explaining where I'm trying to go with things. So the next part then is going to be about this hook formula. So this is one of the formulas for the number of standard Young tableaux of a fixed shape. And I have to explain to you something about what the word hook means in order to introduce this hook formula. So that's what's coming now. So firstly, we're going to sort of need a coordinate system for the boxes in the diagram of a given partition lambda. So there's an obvious way to do that. Well, there's probably more than one obvious way to do that, but we're going to do row I and column J. We're going to give that coordinates ij. So as usual with many of these things, it's easier with a picture. So there's some diagram of a partition, and I've indicated the box with the bullet in is the box with coordinates 2, 3, or in other words, the box that's on row 2 and in column 3. So that's how we'll refer to the different boxes in one of these diagrams. So this would be position 1, 1, and 1, 2, and 1, 3, and so on. Okay, so I'm going to explain about hooks and hook lengths, and the reason I'm going to do that is because these are feature in the hook formula for the thing we want. So firstly, the hook. So this is something associated to each box in a diagram of a partition. So we start by fixing a partition lambda of n. This was our notation, remember? So lambda is a partition of n. And we think about the diagram of that partition lambda. And we think about a particular box in the diagram. So we just decided how we were going to use our coordinates for that. And as I say, each box is going to have a hook. So if we call the box B, or we might name it by its coordinates, ij, associated to that box, there's going to be a hook. And what the hook is it's a collection of boxes in the diagram. And as it says there, it consists of all the boxes in the same row from B onwards. So that means the box B and all the boxes to the right of it in its row, and all the boxes in the same column from B downwards. So again, a picture is going to be more useful. There's it written in formulas, which is probably not very useful, but this just says exactly what I just said. So if B has coordinates ij, you consider ones with the same row coordinate I and any j prime that appears. So as long as these are the coordinates of a box that appears in your partition, and ones, well, either B itself or with the column coordinate bigger than or equal to that of B, so from B and to the right, as I said, and then the union of all those ones with the ones that have the same column coordinate as B and the row coordinate. That's a mistake. So that one there should be an I. Apologies, that's a typo on the slide there. So this should say I prime bigger than or equal to I, meaning the boxes in the same column as B, from B downwards. Let's have the picture, which will be clearer than the formula, especially when there's a typo in the formula. Okay, so here's a picture for a particular example. So here, this time I've taken the box to be the one with coordinates 1, 2. So that's this one here. So we're thinking about the hook of this box here. So the one that's in the first column and the second row, coordinates 1, 2. And the hook is the collection of boxes with black bullets in. So all the ones in the same row to the right, and together with all the ones in the same column downwards. It happens that this is on the first row, so that's the whole column, but had it not been, we would have just gone from the row of B downwards. Okay, so that's the notion of the hook of a given box in the diagram, just captured by that picture there. Okay, and then there's one more part to these definitions that we need in order to understand the hook formula, and that's the notion of the hook length, and that's a number associated to each box in the diagram, and it's just the number of boxes in the hook that we just saw. So we'll write little hb or little hij for the hook length of the box B, or the box with coordinates ij, and it's just the number of boxes that were in the hook. So the size of that set that we just identified previously. So going back to this example, the hook length here is 1, 2, 3, 4, 5, 6, 7, 8. That's the number of boxes in the hook. And we have a hook length for each of the boxes of the diagram, computed as we just saw. So probably that example is there again. There we go. So for example, going back to that same example of a hook for the box 1, 2 in the same diagram that I had on the previous slide, as I just counted, the hook associated to the box 1, 2, which is the indicated one, is 8. It's the number of those black dots appearing there. And you could read off another hook length or any other hook length just by kind of staring at the diagram and writing down the number of boxes in that hook thing that I've just defined. Okay, so now we know about hooks and hook lengths, which means that I can tell you what the hook formula says. So here's a reminder, which I did also at the beginning, that I'm writing F lambda for the number of standard Young tableaux of shape lambda. So this is the thing that I claimed is an interesting number and that we would like a formula for, and here's the first of our formulas. So this is the hook formula for the number of standard Young tableaux of shape lambda. So let's just try and understand what this is saying. So we fix a partition lambda of n, and then the number of standard tableaux of that shape. As I mentioned earlier in the first lecture, the nature of this formula is that it's n factorial divided by something. And what's the something appearing here? So it's the product of all the hook lengths. So if you look at every box, all the possible coordinates of boxes that appear in the diagram, the partition lambda, and for each one of those boxes, you look at its hook length, the associated hook length, which is the thing that I've just been describing, and you take in this denominator here the product of all those hook lengths. And overall, what you do is you take n factorial divided by that product of the hook length. one of the formulas, maybe in some sense the key formula that I want to present and talk to you about. So in terms of how you might prove such a formula, that's something that we're going to come back to in the next lecture. And I've already mentioned that one of the things I want to do is kind of sketch a proof of this hook formula, and it'll be a bijective proof, although it's maybe not a bit obvious at the moment how you could set this up for a bijective proof, but that's what we will see in due course. So anyway, for the moment, we're not going to see a proof of this, but you've at least seen the statement of this hook formula now. Let's do a couple of examples of the hook formula in action so we can see how it works. Just make sure that we understand it, and it should be reasonably straightforward. So there's one simple small example displayed on the slide now. So I've taken n to be 5 for this example, and I've taken the partition 3, 2 of 5. So firstly, we could draw the diagram of that partition. So that would just be the boxes without any entries. 3 boxes on the first row, 2 boxes on the second row. And then, well, I've put some numbers in the boxes, but these are not numbers like the previous ones in the sense that I'm not now drawing Young tableau. And indeed, you can see I've got repetitions. I haven't got the numbers 1 to 5 anymore. Instead, these numbers here in this diagram are recording the hook lengths for each of the boxes. So remember, so for example, in this top left corner, the hook would consist of all the boxes going along to the right along the top row, and the boxes in the below from from this top left box downwards. So we would get hook length 4 here, 3 here, and so on. So what I've done is record the hook lengths in each of the boxes. So I was just looking, there's a question in the chat. So the question asks, what sort of method can we use to figure out what numbers go in which box to ensure a standard tableau? Yeah, so maybe I'll just talk about that in connection with this example. I mean, one can do it somewhat systematically, but I think the main answer is that this is something that one really does not want to have to do, and especially not for n of any size at all. So let me just finish talking about this example, and then I'll come back to that question in just a moment. So firstly, let's just finish this thought that's on the slide about what the hook formula would give for this example. So remember, we're writing f of lambda for the number of standard tableau of the shape. So here the shape is 3, 2, or the partition we're looking at is 3, 2. And it's a partition of 5, and the hook formula says take n factorial, n is 5, so 5 factorial, and divide by the product of the hook lengths. So in this diagram, we recorded the hook lengths, and the ones don't really matter. You can divide by the ones as well if you want, but it won't make much difference. So the non-trivial things to divide by are the hook lengths 4, 3, and 2. So we get 5 factorial divided by that product of the hook lengths. And in other words, 5. To come back to the question, so 5 is a nice small number. So you probably can, and indeed I encourage you to just sort of jot down standard tableau of this particular shape. And you might want to think about doing that a little bit systematically, but it doesn't really matter because I claim that we now know that we're aiming for 5 of them. And with a little bit of trial and error, you'll probably just be able to jot down those 5. And that's a reasonable thing to do in this case because there are only 5. Indeed, I mean, you could even have done something very crude like write down all the tableau of this shape and then just pick out the ones which are standard. Well, that sounds a bit unpleasant because obviously there'll be 120, 5 factorial, 120 tableau, but you can definitely cut things down a little bit, because to be standard, the top left entry definitely has to be 1. You can't put 1 anywhere else, because you have to have increasing numbers along the rows and down the columns. So actually, you would only have to list 24 things if you just list the ones which have a 1 top left. And then you could pick out the ones which are standard, and I claim you'll see that there are 5 of them. Or, as I say, you could just kind of keep track of the conditions and list the ones which are standard. And because the number's very small, you won't find it difficult to do that. Let me have a look at what's going on in the chat. So I think I'll come back to some of these questions a little bit later on. So there was one question about whether it's a coincidence that this is sort of n factorial over n minus 1 factorial. I mean, I guess not. And if you look at the exercises, you will see, I'm not sure if you'll see this particular example, but you'll see that I have suggested that you look for the number of standard tableau for some kind of very special shapes, like, you know, just n, so a long straight one, or n minus 1, 1. And this, I guess, would be an example of n minus 2, 2. I think maybe that one is also there on the exercise sheet. I don't remember exactly. So, I mean, in special cases where you have, you know, a particular shape of partition, maybe with not very many parts, or simple parts, or parts all the same, or things like that, then one can find by fairly elementary methods what the number of standard tableau is without needing, say, the hook formula or something like this. In terms of the previous question about sort of systematically trying to list them, I mean, there are various methods you could employ, and you'll sort of already see the issues even if you do quite small examples for yourselves. But it's, as I say, it's probably not something that you really want to do for large n and complicated partitions of a large n, because even if you try to do it systematically, you're probably not going to keep track really carefully of all the different options, and it's quite likely that something will get missed, and in general things can be quite complicated. Maybe, for example, what's coming, let's see. So here's one which is a little bit bigger. So n is 14 here, and in this example the partition is this one, 6, 4, 3, 1. And here are how things work out, at least if I did it correctly. So maybe I'll just go over what I'm doing again with recording these numbers in the diagram, because one of the questions suggested maybe there was a little bit of confusion about that. So the numbers appearing in this diagram, in each box what's appearing is the hook length associated with that box. So let's pick this 3 here, for example, on the second row and in the third column. The associated hook length is 3, because if we count from here, we would count this box itself and any to the right of it on its row, so another one, and any below it on its column. So the hook length associated to this box here is 3. And for each box we're doing that. We're thinking about the hook as I defined it earlier in this lecture, and then the associated hook length, which is just the number of boxes in the hook. And so I've recorded each of those, the hook length for each of the boxes in this partition here, in this diagram of the partition. And then I've recorded what the hook formula says we should do. So the number of standard tableau of that shape is, well, the n factorial, which is 14 factorial here, divided by all the factorials, sorry, not the factorials, the product of all the numbers, all the hook lengths that appear. So the n factorial over the product of the hook lengths. and it gives a big number. I mean, that's hopefully I did it right, but the point is that, you know, n factorial grows very, very fast with n, and the number of these standard tableaux for a given n and a given partition will typically be some very large number that you don't want to work out by hand, and you want some efficient formula for it. Okay, so for the moment, that's what I'm going to say about the hook formula. I want to talk a little bit about another formula for the same thing. So this is a formula for f lambda, the number of standard tableaux of shape lambda. So the same thing that the hook formula gave us a formula for. And this one calculated via a determinant, so that's a different feature compared to what we just saw. And so I'll talk through what that formula looks like, and then the other thing that I want to do in this lecture is show you that actually the determinant version that we're about to see is equal to the hook formula that we already saw. And then, as I've mentioned, we'll come back to how you might actually prove the hook formula, some sort of intuition for what these hook lengths have to do with standard tableau. That will be coming in the next lecture. Okay, so in order to present this determinant formula to you, we need some kind of standard conventions in order to interpret the formula correctly. So there's a couple of things written here on the slide. This one is kind of standard, I think. The usual convention for 0 factorial is that it should be 1. And so we're going to definitely use that. This is probably much less standard, but it's the right thing here. So it's just a convention. But it turns out the convenient convention to make is to declare that 1 over r factorial should be 0 if r happens to be negative. So I suggest you don't worry about, you know, what the factorial of a negative should be, and, you know, I mean, you should just take this as a convention that makes things tidy in the notation or in the statement of the formula. So that's our convention. 1 over r factorial is declared to be 0 if r happens to be negative. Okay, so having said that, I can show you the determinant formula. So this time, well, I need to have notation in order to write this formula that appears here. We need notation for the parts of the partition. So as before, we're fixing a natural number n, and we're thinking about a partition lambda of n. And in order to make sense of the formula, I had to write down names for the parts of the partition. So the partition lambda, it has first part lambda 1 and then lambda 2 and so on. And so it has some number of parts, which could be anywhere between 1 and n, and we'll call that number r. So this goes up to lambda r here. Okay, so that's just the input data, the partition lambda with parts lambda 1 up to lambda r of n. And then here's the formula, which does require a little bit of interpretation, or just thinking about to understand what it's saying. So it's a formula for the same thing, f lambda, the number of standard tableaux of shape lambda. And it's, well, n factorial times something. And this thing here is a determinant. So I'm using this convention that I write sort of straight lines round a kind of aij to mean the determinant of the matrix whose ij entry is that thing, that aij. So here we mean, think about a matrix whose ij entry is this thing. So 1 divided by the factorial of lambda I minus I plus j, where lambda I was the ith part of the partition. So we're seeing the parts of the partition appear in this formula. And this is going to be an R by R matrix because we have, you know, this lambda I I and j here are both running between 1 and r. So this is an r by r matrix. Okay, so that is the determinant formula. Definitely looks a little bit different in spirit to the hook formula. I mean, we don't see any hooks here for a start. There's nothing about hooks. What appears directly in the formula is the parts, the sizes of the parts of the partition, the lambda i's, and not anything about hook lengths. And then also it's formulated a bit differently because it's formulated in terms of determinant of a matrix. So yeah, let's look at an example of what this formula is saying in action, and then come on to saying something about the proof, or rather, I don't really mean the proof directly. What I mean is the proof of its equivalence to the hook formula. That's the thing that we're going to see shortly. Anyway, example first. So let's just do the one we already did with the hook formula. So we'll go back to this example. So n is 5. Think about the partitions 3, 2 of 5. And so let's just plug in and try to check we understand what the determinant formula is asking us to compute in this case. So, well, firstly, there was an n factorial outside, so that's our 5 factorial. And then, well, it was times the determinant of some matrix, so we're seeing that here. The size of the matrix was r by r, where r was the number of parts. So here we have 2 parts to the partition, so we're expecting the determinant of a 2 by 2 matrix, which is what we see here. And then, well, roughly, what did the determinant formula say? It said sort of the things appearing inside the entries were 1 over something factorial, so we definitely see those, and the somethings depend on the parts of the partition and where the coordinate ij, where you are in the matrix. I'll say a little bit more about how to think about that. Remember what matrix to write down in just a second. Firstly, let's just read through this computation. So the right matrix to write down is the one here, this 2 by 2 matrix. And then we can easily compute the determinant of a 2 by 2 matrix. And what you end up with is that determinant is 1 over 24. And we're seeing the same answer as we saw before, 5 factorial divided by 24, giving us 5. So as we might hope, the determinant formula is giving the same answer as the hook formula, and also, in this small case, an answer that you can just compute by hand anyway. Maybe this is a helpful thing for anyone who wants to play with examples of using the determinant formula. This is a way to sort of remember what matrix to write down. So the parts of lambda, or rather their factorials, they appear in the denominators down the main diagonal. So in this example here, the parts of lambda were 3 and 2, and those are the things, their factorials are what you put in the denominators down the diagonal. So that's why you see 1 over 3 factorial here and 1 over 2 factorial here. And then once you've written those ones on the diagonal, it's easy to fill in the other ones. So the rule is that you kind of increase the thing you're taking the factorial of by 1 for each step you go to the right in the matrix, and you decrease it by 1 for each step to the left. So you fill in the things with the parts of lambda down the main diagonal of your matrix, and then you fill in to the right by increasing the thing you're taking the factorial of in the denominator to the right and decreasing to the left. And it is important to have those conventions about, well, the standard convention about 0 factorial will come into play. It doesn't in this case, but we'll see an example in just a moment. And also that slightly odd convention about negative factorials that I mentioned. I think an example is just coming. yeah, so here's a bigger one just to illustrate those conventions in play. It's certainly easy to get confused about these and get things wrong for this reason. So this example was a partition of 9 given by 4, 2, 2, 1. So the formula says take 9 factorial and then the determinant of the right 4 by 4 matrix. It's 4 by 4 because 4 parts to the partition here. And we should see in action the thing I just said. So down the diagonal, every entry is 1 over some factorial. Some of them are 0 by convention. But everything is 1 over some factorial with those things as the parts of lambda appearing down the diagonal. So 4, 2, 2, 1, that's these denominators here. And then you increase by 1, the thing you're taking the factorial of in the denominator as you go rightwards. That's what you see above the main diagonal in this matrix. And you decrease by 1 as you go leftwards. That's telling you this part of the matrix underneath the main diagonal. And you just have to remember the right conventions, as I say. So at some point you may reach a 0 factorial, which you're going to interpret as 1. And after that, if there's still more room to the left, then you're going to reach something that involves a -1 factorial or a -2 factorial. And then these entries are by convention 0. And that's what you have to put there to get the right answer. I haven't actually worked out what this answer is here, but this example is really here to show you just how to get the right entries in that matrix and to see those conventions in action. Okay, so in the remainder of this lecture, what I want to talk about is why these two formulas give the same thing. So that's the claim. I mean, I've stated each of those as a theorem, and I've given you 2 theorems which give different formulas for the same thing. So the 2 formulas that are now displayed here on the slide, on the left-hand side, this was the Hooke formula for f lambda, and on the right-hand side, this is the determinant formula for f lambda that we've just seen. So on the left, n factorial over the product of the Hooke lengths, and on the right, n factorial times that determinant, where the entries depend on the parts of lambda. So what I'm going to discuss is why this is true, that these 2 formulas are equal, and as I've mentioned, we'll see some ideas of how we get the Hooke formula in the next lecture. Okay, so we need to show this equality then, the Hooke formula equal to the determinant formula. So, well, there's something obvious that we can do, which is just get rid of those n factorials, which appear on both sides. So we might as well do that. So equivalently, what we would like to show is that 1 over the product of the Hooke lengths is the same as the determinant expression appearing in the determinant formula. And just to have some less cumbersome kind of notation, I'll write det lambda for this right-hand side here. So it's standing for the determinant that appears in the determinant formula for the number of standard tableaux of shape lambda. So I'll just write it as the determinant det lambda, the determinant associated to lambda. Okay, so this is what we would like to show. And somehow, well, what's the game plan here? I mean, on the left, we have this formula that involves these Hooke lengths. And on the right-hand side, we have some formula which involves the parts of lambda. So we have to somehow translate from one to the other. And there's sort of a relatively easy thing we can do. So as it says there, the first step is to write determinant lambda in terms of Hooke lengths of boxes. Well, we would perhaps like to write it just in terms of Hooke lengths, but the way this is going to work is that we're going to do the easy thing, which is to write it in terms of Hooke lengths of boxes that appear in the first column of the diagram of lambda. And I mean, I claim that we have this fairly easy relationship to see. So the size of part I, the lambda I, so the size of the ith part of lambda, minus I plus R, which is the number of parts, is equal to the hook length of the box in position I1. So I think I put this as a little exercise on the exercise sheet to do this. It's very straightforward. If you just draw a diagram and remember that if a partition has R parts, then you've got R rows in your diagram, and you just compare the size of the ith part and this particular hook length, which is importantly the hook length for a box in row I but column 1, you'll just see that this is exactly the relationship between those two things. So probably lots of you have just drawn a diagram and seen why this is true while I was saying that. So this is a straightforward thing. So we can, in a straightforward way, pass between the parts of lambda and the hook lengths associated to the boxes in the first column. Well, I guess we need to know the number of parts as well that are. Okay, so using that and just substituting, where I had det lambda written as a determinant, where in this factorial in the denominator I had a lambda I, now I just replace lambda I by a hook length of this sort, an hi1, and suitably adjust. So I'm just substituting this formula here and replacing lambda I by whatever expression in hi1 I have to use. So this already looks a little bit better in the sense that now I have something that involves some hook lengths, but notice that it only involves hook lengths of things in the first column. So what's the plan then? So, well, the general plan is to show the result by an induction on n, and the main step that we'll see in a moment will be to do with removing the first column from the diagram of a partition and comparing what we have for the resulting partition of a smaller number and using that as our inductive step. So we'll see that in just a moment. If we're going to use induction on n, though, we ought to just check some base case before we start. So we ought to just check that everything is fine for n is 1. And that's extremely easy. There's essentially almost nothing to do. So, well, firstly, there's only one partition of 1, which is where you write 1 as 1. And if you write down the matrix associated to that, it's a 1 by 1 matrix with one entry, and you just get 1. And if you write down the hook formula, it just says take 1 over the product of all the hook lengths, but there's only one hook length. It's h11, which is 1. So basically everything is 1 in this situation, and there is not a lot to be done here. So the result is definitely true in a kind of trivial way for n is 1. Okay, so here comes the induction step. We're going to write lambda bar for the partition corresponding to removing the first column of the diagram of lambda. So we're trying to prove this formula, which is about lambda, a partition of n, and we're going to have an associated partition of some smaller number, and it's called lambda bar. And the fact that our inductive assumption is going to be that the formula holds for lambda bar, and we're going to deduce it for lambda. That's the idea of the induction. So notice what lambda bar is. I mean, removing the first column of the diagram. So that's removing one box from every part of lambda. So what you obtain is this partition where you subtract 1 from every part. Some of them, if any of them were equal to 1, then some of these might be zeros and you wouldn't normally write them. So that's, you just, if any of them, so lambda bar could have fewer parts than lambda. if lambda had any parts that were just equal to 1, and then they're just kind of redundant because they're zeros. Anyway, that's what lambda bar looks like. As usual, let's have a picture, which will probably be more informative to see what we're doing. So in the example and these pictures here, I've picked lambda to be the partition 642. So that's a partition of 12, as indicated here. And well, I've drawn lambda bar offset like this because I want to indicate the relationship between the two. Lambda bar is the thing I get when I remove the first column of lambda. So I would remove this first column here, these 3 boxes, and I get the diagram at the bottom. And as I said, the parts of lambda bar correspond to the parts of lambda. I subtract 1 from each of the parts. So in this example, we get that lambda bar is the partition 531, and that's a partition of 9. In general, well, okay, so I was about to say you're going to get that. Yeah, that's right. So you're going to get that if lambda is a partition of n, then lambda bar is a partition of n minus r, because we've subtracted 1 from each of the r parts of lambda. Okay, so we see what this removing the first column thing means in this picture. Let's just think about the hook lengths of these two things. So in the hook formula, we care about the hook length associated to every box in the diagram of lambda. And we've sort of seen in the determinant formula that we can make appear something about the hook lengths associated to the boxes in the first column. And the idea is that the other ones are going to come from the lambda bar. So as said here, notice that the hook lengths of lambda bar, of each of the boxes in lambda bar, those are the hook lengths of the boxes of lambda, but just from column 2 onwards. Let's just go back here, look at the diagram for a minute to see that that's true. So you could imagine, I haven't done it on the slides, but you could imagine putting the hook lengths into each of these boxes, as we saw in previous examples, and removing the first column doesn't change the hook lengths of any of the other boxes. So let's just pick one. Let's say pick this box here, perhaps. So this box here, it has a hook length 1, 2, 3, 4, 5, and its hook length, so the corresponding box here, has that same hook length, because hook length is all about, you know, how many boxes are there to the right of me and below me. I don't care whether or not you've deleted a column to the left of me, right? Doesn't make any difference. So the hook lengths of the boxes in lambda bar are all the hook lengths that we had before, except not those for the first column, because we've deleted the first column. So the idea, I'm going to say a little bit more about this, and I'll end with an example of how this works in a calculation. But the main idea is that we're going to use some row and column operations. So remember, you know, when you work with determinants, quite often you do that. You're allowed to do row and column operations on your matrix, and you kind of know what effect doing those has on the determinant, and you often use those to calculate determinants. So here we're going to play that game in order to show a kind of abstract result. So what we would do is pick some suitable row and column operations in order to prove that the determinant associated to lambda is, well, the product of 1 over the hook lengths of boxes in the first column of lambda times the determinant associated to lambda bar. Okay, and that together with induction, if we can do that, that will prove it. Because by our inductive assumption, this determinant associated with lambda bar will be 1 over the product of the hook lengths for lambda bar, but the hook lengths for lambda bar are exactly all those for lambda, except the ones that we've already put here outside. So we'll get 1 over the product of the hook lengths for lambda. The ones in the first column are out here, and all the others are in here by our inductive step. So if I could convince you that we can use row and column operations to show this, then that would complete the proof by induction of the equivalence of the hook and determinant formulas. So let me kind of really briefly say something about how this works. There's one comment first. So I mentioned that the lambda bar, potentially it could have fewer parts, that the diagram could have fewer rows than lambda. So if you had any parts that were of size 1, obviously when you subtract 1 or when you remove that column, those parts have size 0, they disappear. And you do need to just sort of check how things are working in that case. This kind of relates to those conventions about, interpretations of negative factorials and those kind of things. But it turns out that this still works out okay. So one needs to just check that it's all right, but this is not actually a problem. Okay, so on this slide, I've tried to explain about the row and column operations. And this will probably make a lot more sense when I show you it in a small example in a moment. But let me just talk about this a little bit and remind you about the kind of things you're allowed to do with row and column operations and what happens to determinants. So, well, I'll write Cj for the jth column of the matrix. The first thing that you kind of want to do is just pull out 1 over the largest factorial that appears in each row. So remember that if you multiply a row of a matrix by a constant, then you multiply the determinant by that constant. So we just sort of keep track of that. And this is a nice thing to do in order to pull sort of denominators out of the matrix and have a matrix with integer entries. So that's one thing you can do, and it turns out to be nice to do that. And then there's a process of doing some column operations, as indicated here. So you leave the first column alone. Actually, I might have slightly misindexed this now I look at it. Anyway, I'll show you in an example. So you leave one column alone, you replace one column by its difference from another one, and then the next column you subtract twice the previous one, and so on. And you continue doing these operations across all the columns of the matrix. And at the end, you do a trick where you put some denominators back into each of the rows. So the key things to remember, which you've probably seen when you've studied determinants, is that this thing about if you multiply a row by a constant, then you multiply the determinant by that constant. And on the other hand, if you do row or column operations of this sort, the ones that appear on all these other steps here, those don't change the determinant of a matrix. So if you replace a column by itself minus some constant times another column, that's the kind of operation that doesn't change a determinant. So this is the process. So let's just end by looking at how this actually works in an example, which will perhaps make it seem more concrete. So we'll go back to the example that we've seen several times before. N is 5, lambda's the partition 3, 2, and 5. Those were the hook lengths here. So what's happening in this proof? So remember, the proof had something about sort of treating the first column in a special way. And so we should see some special role of the hook lengths associated to the first column boxes. So that's the 4 and the 2 here. So we should note what those are. And let's think about this process of removing the first column. So that would give us a new partition lambda bar. In this example, it's the partition 2, 1. So it's what we get where we delete this first column of these two boxes here. So we get the partition 2, 1, 3. And let's just go over what's happening in that proof that I tried to indicate, and we should sort of see, at least make it plausible, how the induction step works in this proof. So, sorry, it all came a bit at once, but let me talk you through this calculation. So starting over here, we're writing down the determinant associated to this partition 3, 2. And so the first determinant of the 2 by 2 matrix that appears here, that's the thing that we're told to write down by the determinant formula. And what we're trying to understand is how to express that as 1 over the product of the hook lengths from the first column times the determinant associated to lambda bar, because that's our induction step. So I'm illustrating here the induction step in the proof in this example. So the first thing that happens here is that you pull out the biggest factorials you see in each row. So you pull out a 4 factorial from the denominator in the first row and a 2 factorial from the second row. Make everything an integer, in other words. So that's what you do there. And then you do column operation, and I think I misindexed the columns. I think I wrote C1 where I meant CR, and I somehow counted them from right to left instead of left to right or something. Anyway, what happens in this example is that this column stays the same, and this column, it gets replaced by itself minus the right-hand one. And because it's just a little 2 by 2 case, there's nothing else to do here. So simplifying, we get this step here. And then the final step in the thing that I showed you was you sort of push back some factorials back into the matrix, into the rows of the matrix. What you want to keep outside is so from the 4 factorial, you want to keep a 4 outside, and from the 2 factorial, well, 2. So in this example, all you do is you push a 3 factorial in the denominator into the first row. And the point of this process is that we end up with 1 over 4 times 2 times some 2 by 2 matrix. And if you analyze, perhaps with some slight reinterpretation with the conventions, if you analyze which 2 by 2 matrix you've got, what you're seeing is exactly 1 over the product of the hook lengths associated to the first column boxes times the determinant of the lambda bar here, 2, 1. So to summarize, the induction step of the proof is pull some factorials out of the rows, do some column interpretation, put back not quite those factorials, but exactly what you would have to put back into the matrix in order to leave the hook lengths associated to the boxes in the first column outside. And notice that what you will see inside is exactly the matrix associated to the partition lambda bar, the thing that you get when you delete the first column. So that's what I wanted to say, and that takes us to having seen a proof of the equivalence of these two rather different looking formulas for the number of standard tableau of shape lambda. And what's coming in the next lecture will be some discussion about the hook formula and a bijective proof of the hook formula.